glad everybody made it out. It was for at least me, it was a long flight. How far did everybody come from? Just out of curiosity. Not that far? New York? DC? So East Coast, all right. Anybody kind of local? Huntington Beach. So that's fairly local, right?
80 miles.
Yeah, okay. Very cool. Well, thank you all very much for coming out. It's 8 o'clock on a Monday morning. Nobody really wants to get up that early while they're out here in beautiful San Diego on a dreary day. But I do have a lot of slides. I'm going to try to show you the building blocks for traffic engineering. I want to try to map those building blocks to use cases, and why you would want to do that, why you would want to use the traffic engineering with SR. And then I'm going to show you how to do that same traffic engineering from the CLI that I'm also going to show, do those same policies inside of Crosswork, our automation tool, okay? They are recorded demos, but I do have access to Crosswork, the same platform that I record the demos from. So if anybody wants to change something, we can go in and make some changes and see how that works out for you. But it is a action-packed day, I guess. Lots of slides and pretty good bit of video. Before I go any further, any service providers in here? 1, 2, good bit, yeah, okay. And just everybody else is just kind of exploring SR for the most part? All right, good deal. All right, well, cool. Well, with that, I'm gonna go ahead and get started. WebEx app, go ahead and use it if you're not already. I'm definitely using it. Everybody else is doing it. You can do it too. Just kidding. It's very helpful, definitely. And did you guys notice it does wayfinding? It shows you exactly where you are. Wow, that's how I found this place. All right, so again, the goals, I want to give you a good foundation. I'm not going to show you everything because there's way too much. There's actually a couple of books just on TE, and I'd highly recommend them. If you go and look on Amazon, Segment Routing by Clarence Fizfiz, part 1, 2, and 3. Part 2 is a lot of what I'm going to be showing you here today. Part 1 is also going to be that foundation, where it's just kind of telling you what a SID is and how to use them. Part 2 is how to put them together for a policy. All right, so who am I? I'm Brian Larimore. Thank you all very much for coming. I'm an SE with the IMI team, that's Internet and Mass Infrastructure. I work with public sector and global enterprise and commercial accounts. IMI is also the same team that works with service providers. I just don't work with service providers, the big ones. I work with like Ocean, ARIN, right, which are service providers, and also state and local government. Next, we're going to be doing, like I said, the segment routing primer, and I'm going to try to back it up. There we go. I'll show you a little bit of Crosswork on my laptop, and then we'll start getting into those use cases. Okay. Is anybody doing segment routing today? So you have SR, good. Any traffic engineering with SRTE? None. Oh, you have 1, 2, okay, good. So it might be a review for y'all, but hopefully it's a good one. SR, why SR? Today, in legacy, we're doing RSVP. We have LDP, we have RSVP on top of that, we have the IGP as well underneath all of that. RSVP is very complex, it can be. You end up creating new interfaces, lots of new labels. It can be very, very complex. So we're trying to simplify it. And that's what we're doing here with SR. So at the very bottom of this stack, you still have MPLS. Okay, both sides are going to do MPLS. But as we go up the stack, we see the legacy protocols. We have your IGP, whether it's OSPF or an ISIS. And then we have LDP on top of that, which you have to synchronize with your IGP. And then if you are doing any traffic engineering, you're going to have RSVP on top of that. With SR, everything just goes into the IGP. You have to have that IGP anyway, right, in order to route from one PE to another. Just go ahead and put all that information, all your label information, directly into your IGP. Makes your protocol stack much, much simpler. If you do need to do inter-domain, so if you're having to interconnect with another network, or maybe you made an acquisition, a good way of translating or sharing labels, the old way, BGP-LU, now we have SR-PCE. PCE has always been there, but now we can actually share topologies between the two different domains. For services, getting that service stack. The old way, we have L3 VPN, which is using multi-protocol BGP, and we also have LDP, targeted LDP for your VPLS services, or VPWS, okay? Well, let's move everything into MPBGP. Simplify that protocol stack. Go to EVPN. We don't need the targeted LDP anymore, where you have to manually put in, here's my neighbor IP address. Don't need that anymore. Just plug it into BGP, let BGP advertise it to whoever needs it. Makes it a lot more scalable. All right. So, segment routing is just instructions expressed as labels. The old way was labels, here's how I get to my next hop. That's all we cared about. But now we're doing instructions. Instructions are the foundation for your policies. Here we're seeing ECMP for this particular service. Can you guys see this laser pointer? All right, good deal. So we have a service of 24,001, and we have labels on each P router in the middle. ECMP, the instruction for that one is just go to 21. 21 is here, okay? Then the next instruction is 24,001, which is the service handoff. That's really all it is. That is the only label that you'll see. This is the entire label stack. It does not change until we get to this bottom router down here. Or you can create a new instruction list, make it a SID list, and just give it every single hop in between. 16, 18, 20, 21. There's no swapping. It's just popping along the path. So with latency-sensitive applications, it actually gain a little bit of latency, or you gain a little bit of performance out of doing this, okay? And if any time there's a question, please let me know. I will stop anytime. All right, so the types of SIDs, basic types of SIDs. You have a prefix SID. It's just a label for an IP address, an endpoint, or a PE node. Okay, where's my destination? It's a prefix. I'm going to give it a prefix SID. That is your instruction. Get to that IP address. That's all it is. You also have an IGP node SID. Okay, it's very similar to a prefix SID. It actually identifies a node on your network, which is also what a prefix SID can do, but you can have multiple prefixes on a node. An IGP Anycast SID, if you want to have the same SID on two different boxes for an Anycast gateway, you can do that as well. Okay, we just strip that node SID, the N bit, off the node SID. Then you have these local SIDs, IGP adjacency SID and a binding SID. This adjacency SID says, how do I exit my local router? It is an actual link. It shows you which, it describes an adjacency link out of your network. And then the binding SID, that's the instruction. It's a label for the policy itself, okay? Every single policy is gonna have a binding SID, whether you define it or not, the router will make sure it has one. The great part about it is if you do define it, you can use it. You can now reference that from some other policy, and I'll show you how to do that later. All right. SR, even we call it segment routing, the real name is source routing. It's called source routing because we apply the instruction at the source. As the packet is coming in, like packet X here, it's coming into router 1, it's going to get an instruction that says, go to the endpoint, your destination, via A, B, C. That's your path, okay? That's the instruction. Or we can have packet Y coming into the same router, and its instruction is just get to D. I don't care, just get there. That's ECMP. Now you're gonna follow the IGP, which is the default, okay? A segment is just an instruction. It steers traffic to a specific destination. Here we're showing 17,002. That would be the instruction on router number 1. When the packet comes in, we can actually say, I want to go to take the lowest latency path towards the endpoint that's hanging off of 2, okay? That can be a constraint where we say, I want the lowest latency path. The destination is still 2, but I want to take a different path. There are two different main types of segments, global segments and local segments. Okay, global segments, both are globally significant. Everyone knows about them, but some of them, like the global segments here, they have to be unique throughout the entire domain. A prefix SID is a local segment because you want to have more than one prefix in your network unless it's an Anycast, right? But if a prefix SID is usually tied to a loopback and it's going to identify a node or an endpoint, a destination, and that is going to be a global segment, okay? Here we're just saying like 16,003, notice that both 1 and 2 know what 16,003 is because the IGP is going to be advertising that information. All of this, all these labels, all these instructions are inside of the IGP and they're distributed throughout your IGP. So OSPF, ISIS, that's how these are getting distributed. Both of them, number 1 and 2, know exactly what 16,003 is. It's always going to be the same instruction for both of them, and it says to get to node 3 on this one, okay? This is a very simple example here. Notice that there's a segment routing block. Are you guys able to see this okay? All right. This segment routing block, you can manually define this, but this is the default range. It starts at 16,000, goes to 23,999. That's the default. You can change it. Make sure it is the same throughout your entire network, or you will have problems, okay? Local segment, very similar. Well, like I was saying, that adjacency segment, it's kind of similar to a global segment, except it has a different meaning for every single router, okay? Everybody knows about it. You can still see all those adjacency SIDs inside of your database, your IGP database, but for every single router, it can have a different instruction, different meaning. So here, we have a packet coming in on to router number 1, and the SID is 15,002, which is a local adjacency SID, and it just says exit via link Z. Only one, number 1 here, has a link Z. So they're the only one who can execute that one, okay? That same SID can mean something else on number 2, it can mean something else on number 3. All right, so it's not globally unique. You can reuse it over and over again. That's why we have a much smaller local block. It's only 1,000, the range is only 1,000 on that one. You can reuse it, but it's gonna have a different definition everywhere. All right, your prefix segment, this is usually what you assign to your loopback. Your prefix SID, and it can be defined as an absolute, 16,002, or you can give it an index. This loopback 1. Notice I have 2 different interfaces here with prefix SIDs. You're allowed to do that. You're absolutely allowed to do it. They can be used for different reasons as well. They can be done for some of your TE policies. For whatever reason, you might need to have another loopback with another prefix SID. It can be used for flex algo as well. So this index, for this one, that value is going to be 16,101. The index is an offset off of the start of your range, okay? Router, if you do ISIS, this is how it would look inside of ISIS. So you have your loopback, it's passive, your IPv4 unicast address family, index 2, so it's 16,002, or you can do an absolute 16,101, okay?
Loopbacks would have IPv4 addresses?
Yes, yes. Yes, yeah, they will. Yeah, they're gonna be defined elsewhere in the config, yeah. Back to binding SID, it's a local segment. Remember I was saying a local segment is gonna have a different definition on each router. It can be the same definition if you want to do that, doesn't matter. But it is always going to represent a different instruction. The great part about that is, like I said, it's advertised to all the other routers throughout your IGP domain, so anyone knows about it and can forward to it in order to execute. So here we have a packet coming in at 1, all right, and we can push 15,006 onto the stack to make it get to 5, and once it gets to 5 knows what 15,006 is, and it says we're gonna push on a different stack, a different label here, 20,006 in order to get over to here, and it's also gonna do lowest latency, all right? 15,006 at 1 is not going to say get to 5. We need another prefix SID on top of that, so it'll be 16,005, 15,006, and then when it gets to here, from the 16,005 instruction, 5 will then execute 15,006, which says push 20,006 on, and that instruction is follow the lowest latency path to number 6. Does that make sense? Okay, I got some head nods, that's good. All right, another good thing, so this here is what I would kind of say is kind of like a proxy server, if you think about it. Or maybe you have, these are all XE boxes, and they can't do a big label stack. Or maybe you just have another router on your network that can't do a really big label stack. XR, I deal a lot with XR routers, iOS XR, and we can do 10 labels in the stack. XE can only do 3. That's a problem if you're trying to do traffic engineering and you have Catalyst routers in the middle of your network. So what you can do is just assign a prefix SID that says get to an XR box, and then assign that local adjacency, the binding SID, which then execute a new policy, which could be really big, and send it on through the rest of your backbone network. All right? It's a way to scale up your traffic engineering policies. Adjacency segment. I like these. They're used a lot. Okay? Dynamically, every single link will be assigned an adjacency SID. It is a local segment on every router, but you can also manually assign them for your policies. It identifies a specific link or an exit point on your router. Okay? It will override your IGMP, or sorry, not IGMP, your IGP. Got multicast on the mind. So maybe red or the green interface here is 100 gig, and red is 10 gig. IGP says exit out of the 100 gig. Well, maybe this is a flow that you just don't want to go over that. Maybe it's some type of backup flow that you just don't want to go across your 100 gig for whatever reason. Maybe that's production traffic and you just want to use that 10 gig for your backup. You can say that you can define that backup flow to take the red one by just assigning this 15,002 adjacency SID to its policy, and it will exit out of that other slow link and go towards 2. It'll also, if this was a bundle, Ether channel, you can also do the same with that one. So there's 2 members of a bundle. You can manually say, I want to use a specific member of a bundle. In case you have an elephant flow and you get hashes to one side, you can kind of, you can dynamically, through your policies, you can actually create a policy that will force other flows to go across the lesser used link on that bundle. All right. This is how it looks. So in OSPF, you have your prefix SID. Then inside of your interfaces, you can come in and say, all right, I want to create an adjacency SID, and it has an absolute value of 15,001. Or you can also do that index, that offset, same as the prefix SIDs. So you're just assigning an adjacency SID to the interface themselves in your IGP definition. That's for OSPF. And I thought I had ISIS. I apologize. There is one for ISIS coming up, I'm sure. But ISIS is very similar. Inside of ISIS, when you define your, when you activate your interfaces in your ISIS router configuration under address family IPv4, you'll just assign that adjacency SID under that interface. Okay. All right. Segment list. Now we're going to get into the actual policies. We want to create a segment list that says, I want to go a specific direction. It's just it is literally a list. It's a SID list of different SIDs, okay? Each node is going to execute the SID that's on top. So you have a label stack. It's going to take a plate off the top or a SID off the top of that stack. It's going to pop it. It's not going to swap it. It's going to pop it by default, okay? And then pass it on to the next router, pop. Pass it on to the next router, pop, okay? And when you're creating them, the one is going to be inside of your config is going to look like it's going to have an index. Okay, so index 10, that's the one that's on top. Index 20 is right below that one. Index 30 is whatever number you want to give it, but the lower number is the one that's sitting on top, and it just numbers its way down, just like an ACL. Something else we can do with constraints. Constraints are ways of dynamically assigning a path. Okay, we can each router is going to execute according to the constraint that's presented to it, like the lowest latency constraint. It's going to look at its path from its perspective. What is the lowest latency path to the destination? It's going to select that path and exit. Okay, and the PCE can be used to push new path destinations or new paths down to the router, because it kind of knows about that topology and also knows about the topology of the other domain that you may have. So it can see the destination IGP domain and decide, hey, the best path to the destination, even outside of my network, into the other network, I can now, it knows that, so it can create a new path through your network to that destination based off of that constraint. That was really confusing. Let me try that one again. I'm here in my network. I need to go over there. Maybe the lowest latency path out of my network is path A, but the lowest latency path through the other network, the other domain, is path C. I will, instead of going path A and then let path A continue through their high latency domain, I can find a new path to their path C inside of my domain and exit out that way, okay? I can now see both domains with a PCE. All right, so the lowest latency constraint, how do we build that out? We're going to just, we have a binding set. I'm manually assigning that one, 15,110. I do not have to manually assign that. The color, so every policy is defined with a head end, a color, and a tail end. That is the definition of a policy. That's how it is identified, on the network. So we assign a color, then we give it an endpoint. It already knows the head end because it is the head end. We give it an IP address for that endpoint, and then we're going to create some paths. Right? The candidate path here, we have multiple preferences. This one is only one preference, preference 50. The higher the preference, the more likely it's going to be used. Okay, that is higher is better. We're going to now say it's dynamic. It's a dynamic instead of a static SID list. We're going to use a dynamic path, and the metric is going to be using latency. We can also use IGP, which is just the IGP path through your network, or you can use a traffic engineering metric as well. So when you, just like with RSVP, you could assign a traffic engineering metric to your policies. That same metric can be used in SRTE. All right, so that link constraint. We also have this one. Link constraint says that I want to use a specific link whenever I'm going through the network. And like I said, it overrides the IGP. This one here is actually using the adjacency SID constraint. You can do affinities as well. So you can say dynamically, I want to always follow the red path. Here we're saying I want to follow 15,001 out of this router, and then the next one will say I want to just get to 16,002. So here's this policy, the binding SID, 15,110. That the first label is 15,001, exits out of this adjacency SID, and then the next label, and it's going to pop it. It's going to pop 15,001 as it exits out. Then 3 is just going to have 16,002. That's the next instruction. And it's going to say, okay, just get to 2 however you can. So if we had multiple ways to get to 2, it would take the best path that the IGP stated at that point. Does that make sense? All right. Okay. Other constraint types. Yes, sir.
So if you were to set a policy on something, is the default to, let's say that path is unavailable, is the default for it to fall to the IGP, or will it fail?
Great question. So let's back it up, because we actually had this yesterday in my lab. All right, 15,001, if that does not exist, it will fail, okay? It will drop it. But if we were to say 16,003, if that was the first one, instead of the adjacency SID, it was a prefix SID, it would go to 2, then to 3, because there's another way to 3. And then it's going to go back up to 2.
So is there a way to set up a active protect scenario in that scenario where you can sit there and say, use this segment list?
Yes.
All is well with the world?
You would create another preference path, another path. That's all you have to do.
It would just be another preference.
Yep.
Like
It'd be a lower preference.
25, basically.
That's exactly right. Yep.
One other question.
Yes.
You mentioned that the XE routers only have 3 labels, you only support 3 labels?
Yes.
What happens if more labels go?
That's a great question. I haven't come across that one yet. I don't know, because at that point, the header's too big. I think it would drop it. Yeah. Yes, sir. Absolutely.
So if you did another preference 25 and you just wanted to follow the IGP, worst case scenario, you just don't have a second list. You just
That's
do a
correct.
preference, nothing in it,
You would have,
some other command to say follow the IGP.
absolutely. So instead of this explicit, you do preference 25 and then just say dynamic metric IGP. Done. Yep. Yes, sir.
Are the constraints defined to each one of those hops, or are they just at the beginning and based on
Great question. So you can put, 3 knows where 16,002 is. So it doesn't need to have a new definition. It's just going to follow the instruction. We're defining the definitions or a path here, and each router just executes that instruction as it sees it. If it doesn't have a 15,001, like we said earlier, it's going to drop it. But if it does have a way to get to 16,003 and 15,001 does not exist, it'll go to 2 and then go to 3, and then 3 will then execute its next instruction. Does that make sense? I'm kind of, okay, excellent. All right, thank you. All right, other constraint types. Link avoidance. Instead of saying I want to use 15,002, I say I don't want to use 15,002, okay? Node affinity. I want to always go through a specific router in my network. I don't care how I get there, I just want to make sure I flow through it. Maybe that's your NetFlow router, the only one that supports NetFlow for whatever reason, okay? I always want to go through that one. You can do that. Node avoidance. Node avoidance is really, really big for TDM circuits, okay? If you're trying to emulate TDM, I don't want to use the same path that another path that I've set up is using, like a protect path, all right? SRLG, shared risk link group. If you are using if you have 2 different interfaces on a router that are in the same fiber bundle, that's a shared risk link group, okay? Now those are the same, essentially to the router, they're the same link. I want to avoid this link and go out of another one that's going out of another strand of fiber, another path in the conduit in the ground, okay? Bandwidth, that's another one. So bandwidth is, we can reserve bandwidth. We can say this particular flow needs at least 1 gig of bandwidth. That's great, we can do that, but you have to have help. The routers are not gonna be able to reserve bandwidth end to end on a path. We need another compute node above that can see all of that and push down a path according to that reservation. And that is crosswork. We have to have crosswork in order to do that. All right, quick crosswork primer. I'll try to run through this. If you don't mind, just kind of hang out with me just for a second while I log back into it and then switch over. How's everything going so far? It's all right? Okay. If, something you want to see, just let me know.
These dynamic constraints like delay and bandwidth, crosswork periodically surveys those interfaces or links, or it's like the HRP, like when you turn it up, it measures what it was at that moment, and that's what it is.
Really good question. So a dynamic constraint like latency and bandwidth and utilization, those are constantly being updated by your IGP. Yes, and your PCE can collect all that data and define a new path, or the routers themselves can see end to end on that one what is able to be used.
Are we going into the PCE portion later in this?
Not really. I can jump into it if you want.
Well, my question on the PCE was like, is that pushed by dynamically, or is that done as like router instruction as opposed to the grid setup?
It is done dynamically. So the PCE is usually just another router on the network, and it's using the PCE protocol. It's NetConf essentially.
But it's not making a config change to the router. It's still
It can. It can push config.
Not a sync with the server?
No, so when it does in that config change, it's not a actual configuration. It's not doing a commit or anything like that. It is going to push down a topology, and it's going to go into memory. And that memory is going to be defined. You can actually do a show segment routing traffic engineering policy, and you'll see it. But if you do show run segment routing, you will not see it.
Okay.
Yep. All right, you guys are able to see this? So this is crosswork. Anybody familiar with crosswork already? Yep, okay. We have one. Oh, sorry. Okay, so this is crosswork, and we do have a topology. We have multiple devices on this one. This is not my server. This is our TMEs. They don't know I'm using it, so shh. They have a lot of different nodes on here. We can actually see XE and XR boxes on here. There's also a Juniper MX, virtual MX in here. And hey, Mark, how you doing, bud? We have, so this is the topology. We can come in here and click on links and see what's going on in each individual link. So layer 2, IPv4. We can see the A side and the Z side, and if I zoom in here, you can actually see it a little bit better. We have an A side right here and a Z side, and we can start to see a little bit more information on this. this link. We can see the delay, we can see jitter. All this is really good information when you're designing your networks, and you need to need like a voice network. You don't want jitter on that one if you can help it. We can see every bit of that. And then if we go into, this traffic engineering, now it's going to give us a different context. We can now click on the same link with traffic engineering enabled, and we can start to see this IPv4. Now we can start to see a little bit more under traffic engineering. We get that tab up here now, and we can start to see adjacency SIDs. And you're going to see this in the demo videos. So on the Z side, which is over here on node 2, I have some SIDs. I have one that's manually defined, 15,004, and I have some dynamically assigned ones here, and some of them are protected, some of them are unprotected. And unprotected means if you're doing fast reroute, then you don't need to, I don't care if I have a fast reroute route in my network, okay, on that particular link. So you don't want that. You don't want to do a fast reroute if you want a statically assigned path. You don't ever want it to change, so don't fast reroute it. Just go ahead and drop it, and we'll find a new path, okay? All right, that's it. I don't want to show you too much here, but is this enough for you guys? You guys kind of seeing what we need at this point? I can show you more later on. That's hopefully the plan. All right. Okay, so use case number 1 is just a SID list. Very simple. It's the simplest one to do because you're just creating a list and saying, I want to go hop by hop by hop, okay? We can do a link affinity. We can do node affinity with this one. We can do, it's often used in circuit style traffic engineering policies. Circuit style is going to be use case number 2. It is just saying, I want to emulate a TDM network, a frame relay, a SONET. I want to emulate fiber channel as well. You can do all of that. Those types of paths, we can emulate those with a statically assigned path through the network. But with circuit style, you have to add another path, a protected path. Okay, so you have working and protect. All right, back to the SID list. This is how we do it. We kind of went over that earlier. We're just going to assign some SIDs, 17,003, 17,002, and 1 is going to execute that one, pop off 17,003, pass it to number 3. 3 is going to pop off 17,002, pass it to number 2, and off it goes. Yes, sir?
Is it possible to do something like ECMP?
This is overriding ECMP.
So there's no way to say go through 2 paths?
You can. So that's a great point, actually. I can, if there were more nodes in here, in fact, I can show you in the demo. I can say, all right, if there's another way to get to 3 that is ECMP, I can just say, go to 17,003, and it will take ECMP to get to 3. If there's a second path, it'll take it. If I want to take a specific path, then I assign an adjacency SID. But if I'm using a prefix SID, which is what I'm doing here, that's a global segment, 17,003, it will take ECMP. Yep. Okay, like back to this one. If I just kind of explain that one. If I want to take a specific path to get to that same link, that same destination, I would use an adjacency SID. And that's what I'm going to do in the first demo. All right, this is how it looks in OSPF. Kind of went over that earlier. And all right, so demo use case number 1. We're going to try to play this video. Yes? It will, yes, it will definitely assign them dynamically, but if you're going to use them in a policy, don't use the dynamic ones because on reboot, it gets a new dynamic number. Yep.
Would you use the PC, it would be aware of those?
Yeah, but it still wouldn't, if it's making a dynamic policy, yes, you're fine. But if you're using an explicit policy, it could fail.
Right, okay.
Yep. All right, so, trying to see, there it goes. So what we're doing here is this is the path that's set up. This is the IGP path from node 2 up to node 4. Can you all see this okay? All right. And what I'm going to do is I'm going to say I want to use a different path, which is that one I was investigating earlier. I want to use node 2 to node 6. And I want to go 6 to 5, which is further up in the network. And you'll see that in a little bit. But this is how you set it up. All right. So I'm zooming in, and I'm showing you this because you don't have to use the CLI. You can use the GUI for every bit of this. For me, CLI is a little bit easier, but the idea is that you don't have to touch CLI anymore, okay? So here I went to that traffic engineering context. I got the adjacency SID that I wanted, which was 15,004. And then I'm going to go and actually create the SID list. So I'm going to provision through NSO. I'm going to scroll down to a SID list. We're going to create the new SID list. I named it CLUS, and it's really hard to see, and I apologize for that, y'all. But it's a CLUS SID list, and I'm going to give it an index. Index 10, index 20, index 30. It's your ACL. You're just building that list. Remember, the one with the lowest number is going to be the one that's popped off first. So that first one, I said 15,004. That's my adjacency SID that I just found. And my next one, I wanted to send it to node 5, so I put in the prefix, put in the prefix SID for node 5, which is 16,005. That means I don't care how I get to 5, just get there. And then finally, I want to get to node 4, which is my destination PE. Again, 16,004. Just, I don't care how you get there, just get there. So it's a very simple list. Just wanted to show you this is how it's done. This is just assigning it or creating it inside of Crosswork. We're not actually pushing anything down to the router right at this time. With that commit, nothing happened. It's all inside of Crosswork at this point, just in memory on the server. Then I go up and I create a policy at this right now. So here I create that policy, give it a name. This is a friendly name. This is not the official name, like what the router is going to install inside of its tables. You'll still see the friendly name inside the config, but you will not. It'll also have the IETF standard name as well. The head end is node 2, and then it needs to know the IP address of the tail end, which is coming up next. Because there can't be multiple IPs on that tail end, so you just give it the loopback that you want. This is the simplest way to do it on this one. I'm giving it a loopback of 1.4. Create a color. I can make this one, for this one I'm going static. So I did 6132. I can create a binding SID. You do not have to do that. The router will do it for you. Since I'm not going to reference it anywhere else, I'll just let the router do it. Then I just I create a new path preference, 200. I give it a preference of 200. I said it's going to be an explicit path, and I referenced the SID list that we just created earlier. Okay? And then I commit that. There's a lot more you can do in there. As you can see, they have performance measurement, circuit style, other constraints. I opted not to use those for this one because I wanted to keep it easy. Now it's pushing out to the routers. It's pushing down the SID list, and it's pushing down the policy. Now if I go and click on it, it will pop up the traffic engineering topology, and it will show you the new path. Originally, the path went through node 7 down here at the bottom. Now it's going to node 6. And it shows you the path right there that I explicitly set. It shows you that it's active and it's up. If it's not up, then traffic is breaking at that point. Okay? If it doesn't have a path, it will break. Now I'm going to show you the CLI, show you how it came in. So first, I'm showing you the JCC SID index 4 for that particular path. And then I'm showing you the SID list that got pushed down, index 10, 20, 30, and the list themselves, or the SIDs themselves. And then I'm going to go down and show you the policy that was installed. 6132 is the policy. Pretty simple from a policy perspective. See that name? I highlighted it for you. That is the IETF standard for naming of a policy. It pushed that one down. You still have the friendly name inside of Crosswork, but it pushed that policy name down. You can give it any policy name you want, but that's what Crosswork pushed down. Okay? Any questions? Yes, sir.
Somewhere in here, I assume you can write a class and define what is going to take its path.
Yes.
Always from this
Yes.
to this.
And that's a good point. I did not assign this policy to any service, but it's showing us before we assign it what that path is going to be. But yes, I can create a policy, a route policy that says based on DSCP value EF, I want the traffic to take this policy and follow that path. Everything else, I don't care how you get there. Yep. Any other questions? Say again?
How do you bind that to an L2VPN?
With a pseudo wire class. Yes, and we'll do that with FlexAlgo in a little bit. Yep. He asked how to bind it to an L2 VPN service, and you do that with a pseudo wire class. All right, any other questions? All right, yes.
Well, you said that if the LSP doesn't create because of some problems with the SID list, perhaps reachability, are we then saying that the LSP is broken, or does it then, like, traffic just gets platformed?
Good question. So he was asking if we assign this policy like we did earlier and that policy gets broken, that path is broken, are we saying the LSP is broken at that point, or are we just black holing the traffic? We're going to drop that traffic. There is no LSP at that point. There is no valid path. Yep. Even though there is a IGMP is a valid path, policy says no valid path.
Best practice is to put in a catch-all,
Yes. Well, it also depends on the traffic flow.
or you don't care.
Yeah. If we're talking about like top secret routing, we don't want it to go somewhere else first, right? It just depends on your particular requirements. Yeah. In fact, with circuit style, which is the next one, we're going to have that fail all, that catch all, in there. Any other questions? Okay. All right. So use case number 2 is going to be circuit style SR. Okay, this is emulating TDM, Sonnet, whatever you need that needs to have a working and a protect path. That's really what it is. They're going to have link affinity. They're going to have node affinity. We're going to have leak avoidance, node avoidance, SRLG, disjoint. Disjointed is that working path and the protect path. They are disjointed from each other, and they're co-routing. So that means the path that it goes to get there has to be the same path on the way back, on both working and protect. That's your co-routing. All right, here comes this demo. And let me press play. All right, same thing here. I did pull up the EVI. I don't think you need to see that one right now. So I'm going to go in and I'm just going to start creating a circuit style policy. I don't need to investigate all the different adjacency SIDs or prefix SIDs. I just need to know the endpoints for this policy. It'll figure everything out for me. So I'm going to give it a name. I gave it a friendly name, CLUS, CSSR 2 to 4. And I gave it a color. Should try to put a color in there just so it's easy to identify for yourself later on. All right. I am going to manually identify a color so that I can go and grab it later. I could we can pool these numbers. We can create pools and just let it auto-fill on its own. We can do that with EVP and EVIs as well. But here I wanted to manually assign it. I'm also assigning bandwidth of 500 at the very top. Kind of talked over that. You have to assign bandwidth for a CSSR policy. If you don't want to assign bandwidth, then just create a SID list. A couple of SID lists that are co-routed. You can also create dynamic lists that have disjointed paths and co-routing on them, okay? And here's where you start to do that. So you will create, I'm going to say I want to avoid the nodes with this group. I want to make sure I avoid going through the same nodes on the paths. And I'm going to give it a group ID. This group ID is the disjoint group ID. All right, you just give it a number. It's kind of arbitrary, but it has to be the same on each side. So that way they know I need to avoid these paths. Need to avoid each other. I gave it a latency metric type for this path. This is for the working path. I have to give it an unprotected segment. That means each layer 2 segment is unprotected from a routing protocol perspective. I don't want it to fast reroute if there's a failure. If there is a failure, just leave it be, go to the protect path. Bidirectional association, that's your co-routing. That's coming, is getting that from a pool, but it's just a number. And it's something that I'll show you in the CLI when it's all done, how that's used. Revertive. If the working path dies and we have to go over to the protect path and the working path comes back up, do I want to fail back over? And how long do I want to wait before I fail over? The default was 5 minutes, 30 minutes. Now it's going to be 10 minutes. All right, so the restore path. I think that you were asking what happens if it all else fails. What do we do? That's what that restore path is. It's just going to create a path that says just get there, ECMP, best way I can. You do not have to do a restore path if you don't want to.
How do you figure out the forwarding path from either CLI or this?
I can show you in just a little bit. But for this one, for a CSSR, it's going to create a SID list in each path, in each direction. But you can do show segment routing, traffic engineering policy, and then define the color in that show command, and it'll show you everything, that entire path for you. If you want to go hop by hop, you can do show Ceph and give it the IP address and everything, and it'll show you the path out of the box according to the policies. So this is one path. It is co-routed, has arrows on each end. That's one path that it created for this particular, that's the working path. And I'm over here showing you this is the path here. These are the adjacency SIDs that were used in order for this to work. Those adjacency SIDs were previously defined on the router, okay? Now I'm showing you the protect path. And there's the adjacency SIDs. And you can actually visualize all those paths. I don't know about you guys, but if I'm an operator, I don't want to sit there and go hop by hop if I can help it. I love the fact that it can visualize it for you. So now we're showing you what was inserted. This is, we're going to get down to the path itself, or the policy, and see where everything came in. So here we go. 6134, right? Yes, good. So it's locking it. That was the revertive stuff. The preferences. So this is the preference, the highest preference on the. This is the working path. It shows you the disjointed group that was assigned to it, 601, bidirectional. The 601 and that 601, two different 601s. Okay. I wish they hadn't have done that, but they're the same. They overlap on the pool. But that just says this disjoint path for preference 100 and preference 50, which is working and protect, avoid each other. Because they're the same disjoint path group, avoid each other. Then bidirectional 603, that means I want to make sure that it is on each end, you'll see 603 on the other side of the path. So in node 4, you'll have a bidirectional ID of 603. That means I want to use the same path for the reverse traffic. And here's that traffic engineering policy, and I can define the color. And here is the paths. They're the same ones that we saw visually inside of Crosswork earlier. So you're working, it's right here. It's active. I'm going to pull that down so you can see all the SID list. Here's all the SIDs here that we talked about. The reverse path, this is installed on the other router, on the other end, node 4. And I'm just kind of showing you, hey, look, all these numbers line up. Yes, sir.
Question for you.
Yes, sir.
Distribute link state under ISIS is needed for the PCE route.
Yes, yes.
You add it to the others, or?
You want distribute link state on every router to distribute its link state to the PCE. Yeah.
Why do you need every router when one router will have to?
So it's saying I want this particular node, like node 1, I'm going to distribute my link state. I'm going to distribute my latency, my utilization, everything to the PCE. The PCE is trying to collect as much information as it can, so it needs everybody to share their information. And that's it. That's what distribute link state is for, is to share that information. All right, so that kind of ran through. Hopefully, did y'all see what was going on there and how it worked? You want to investigate further? I can get into either the CLI or the GUI if you want to. No? All right. Oh, it's still going. My goodness. That's why you're laughing at me. I like that. Yeah. All right, so I think, am I on node 4? Yeah, so I'm on this node over here now, looking at the same stuff, showing you that it's configured the same way, and yeah, the bidirectional and the co-routing or the disjoint path are the same. All right.
Is there any potential for having a policy go from A and B, but then also having a policy for services that terminate between A and B to take different paths?
Yes.
And then it's based on specificity, right? So the service governs that.
Yeah. So for what you were saying, we could attack that a couple of different ways. If you have other traffic, like you said, traffic for another service to terminate somewhere else in the network, we would assign a different policy to that service. So that's how it would terminate somewhere else and have a different path than all the others if you wanted to. So as long as they have the same bidirectional and disjointed IDs, then it will take different paths. So if you say that I want a disjoint group of 601 for one service, and I have another service that I just don't want to take that same path, you could assign it 601. And it could be completely different routers and services. They'll still avoid each other.
I don't mean between two services. I just mean one PD to another as having a different forwarding path defined than a service going from that same PD to a different.
Okay, so you're saying you have one service from one PE to another PE, and you have now a second service from those same two PEs?
Another TE policy just for all traffic from PE1.
Oh, so all other traffic, essentially.
I'm just wondering if there's a scenario where if you can have a TE policy for one PE to go to another, like all traffic gets forwarded from, going from left side versus the right side. But then you have something more specific where you have a service that goes from that PE to the other PE and it goes to the right side.
Absolutely, yeah. Yeah, so back to your pseudowire classes. You can reuse the same pseudowire class over and over again, and that would be for all services that you don't care about, I guess, and that one service that you have to have a specific path, you would have a different pseudowire class for that one. Is that what you're asking?
Yeah, so I'm just thinking like operationally when you're trying to troubleshoot the forwarding path, it's you have to go on a per service basis there. And we don't have every time.
Yeah.
It's like, so depending on the size of your network, if it's something simplistic like a hub and spoke, or maybe a partial mesh may be easier. I just can't imagine effectively running the network if you have so many different policies without some kind of controller.
Yeah, exactly. Yeah, if you have a really large network with a lot of policies, you want a controller if you can help it.
So on the controller itself, is there a way to say that for this service, to go from A to B, it's taking that forwarding path?
Yes.
And you can see that, like I think we saw the SID list, right? Is there a way to see that on, let's say, the signaling plane and the bearer plane?
I'll have to get back with you on that one. I want to make sure I'm understanding your question a little bit better.
Yeah, so
Yeah.
like you mentioned being able to do like show SEF.
Yes.
Show SEF hardware. Like, is there like that kind of visibility on crosswords?
Not show Ceph, that you're really getting down to the, Crosswork is going to be showing you what it interprets as the policies that are active at that time, and the inactive ones, the ones that have been programmed into the router's memory. And that's what it's going to be showing you.
You mentioned that before, routers memory. So when you said we did a commit on crosswords, did it actually push that to the router?
Here it did. It pushed it out to the router. But there is a way to do a PCE initiated policy. These are PCC initiated policies where the client is initiating those policies. But you can have the PCE initiated policy as well. It'll build it in the PCE, and then the PCE will use PCEP to push that out to all the routers, but it's just going into RAM. It's just going into its memory and into the MPU. It's not going into config.
You define the policy on the PCE.
Yes,
And then
yes.
you go under that and just the dynamic, you assign that to PCE, right?
Well, when I did PCE there, that was saying use the PCE to help build the path. But there is, you can, let me see if I can pull that up. Inside of Crosswork, you are actually able to create, sorry, it has to rebuild my VPN. You can tell it I want to create a PCE initiated policy or a PCC initiated policy. It's just a different way of going at it. The way I'm doing it through NSO is always going to be a PCC initiated policy. But there's another way to create these in another location. It says I want to do a PCE PCE initiated policy.
Is that the intent of the PCs to have that logic inside?
It's some of it. The biggest intent is to understand the entire topology of the network. That's what it really wants to do. It wants to know this network's topology and whatever other networks, other domains, it wants to gather all that information as well. That's the biggest intent. But then you can tell it, hey, I also want you to push out new paths, but I don't want you to change the config.
So what would be like the decision making between like a PCC determined path versus a PCE? Like what would you?
I've seen that one. The PCE path is going to win.
No, I'm saying,
Yeah.
I'm like, well, from your preference, like it sounds like you can do it two different ways, but like.
Right. For me, my preference, I want to see it in the config. That's the way I am. I'm still a CLI guy at heart. I want to see it there.
That would be the PCC.
Yes, that's correct. Yep.
Okay.
Yep.
One question I have.
Yes.
Does Crossroads support all of this stuff, policy creation, the affiliates, the OS, for non-Cisco routers?
Yes. Yes, it does. There, can't tell, but I think it was this node. It was not showing it. Node 19 down here, I think, which is way out of nowhere. It is a virtual MX Juniper router. Yeah, we can, as long as we have a NED for it, for NSO, because NSO is running everything on the back end of this. As long as we have a NED for it, we can control it. Yep. Any other questions? I'm going to move on to FlexAlgo, which is, we raised the bar a little bit. Okay. All right, FlexAlgo. All right, this is intent-based traffic engineering. All right, software defined, if you want to think of it that way. We're going to advertise the intent by BGP, okay? The path is always going to be dynamic. It's going to be based on a calculation type. These are your calculation types as of this writing, IGP, traffic engineering, and delay, okay? Every router is going to advertise its participation in an algorithm. There are 255 algorithms. The first 128 are reserved, can't use them. 0 and 1 are already in use. 0 is IGP, follow the IGP, however you can get there. 1 is strict SPF. That means go there, and if you break anywhere along the path, drop it, okay? You cannot override the IGP at all. If you try to, if it'll break it, it'll drop it. Okay, that's number 1. 128 through 255, those are the ones that you get to play with. Okay, so there's a little bit of a scale issue there. If you have a whole bunch of algos that you want to have in your network, you only get 128 of them, or 127, I reckon. And the algorithm number, it has to have the same metric. So you have that metric of IGP, TE, or delay. You can assign that inside the routing protocol when you're building it, and it has to be the same everywhere. Okay, so if 128 is IGP on one router, it has to be IGP on another router. Sometimes you mess up and you put latency over there, delay. So now you have a priority. You can actually build in a priority on that as well. The priority that is advertised as the highest priority is going to win, and it's going to override the IGP or the latency one over here if that had a lower priority. Okay, does that make sense? Okay. All right. And like I said, the nodes advertise their participation via the IGP. Okay, and I'll show you all that in the config. And one node can participate in multiple algos. You can participate in all of them. They're already all participating in 0 and 1 right now. Any of your custom ones that you build, you can participate in multiples of those as well.
And the loopback can participate in different.
Yes, yes, you'll see that config. Absolutely, great question. A loopback can be in multiple Flex algos, but they're all gonna have their own prefix SID. Yep. And BGP can share the Flex algo assignments between routing domains, okay? All right, so the calculation method, SPF or strict SPF. You cannot override with a local policy with a strict SPF. And then your constraints. These are exclude any, down at the bottom, exclude any, include all, or include any, okay? So a link affinity on that one. If I want to exclude all red links, you're gonna, every time it gets to a router, even if red is preferred path from the IGP perspective, if you said exclude all red links, it's not gonna go across that red link, okay? If you wanna include all red and green, it'll take either red or green on that router. If red or green do not exist, depending on the rest of your policy, it may drop it, but usually it passes it anyway. you'll find another link. Okay. The role of BGP in Flex Algo, like I said, it advertises. It's going to advertise a color through a routing policy. It's going to advertise to the far end the policy that it wants the far end to use to get to it, okay? So Brandon over here, he's my WebEx moderator. He's my far end. He wants to send me something. I'm going to tell him how to send it to me, okay? I want you to send it via UPS, please, sir, right? I might go to John and say, I need you to send it by FedEx. So BGP is advertising that preference, and vice versa. You guys are going to advertise back to me, okay? And you can then assign either a nested route policy. This is best practice, route policy outbound advertisement on your L2 VPN, EVPN, SAFI. That's a big mouthful. I'll show you how that looks in just a second. You assign an opaque external community to set that color, okay? So on the right-hand side over here, right, yeah, it is right. This is my opaque color community. I'm just saying 6133. That's going to be the color I'm going to use for that policy that I'm going to eventually build. Then I have a route policy to match the routes. Okay, here I'm showing, this is an RD for an EVPN. That's all that is. It's 192.119.1.2. The 200 is the EVI for an EVPN. Does that make sense? All right. And we also are matching the same with 198.19.1.4. I'm just saying that this same policy is going to be used on the head end and on the tail end. I can definitely narrow this down as much as you want to. I can make it much more specific, however I need to do it. But I decided I'm going to use the same policy on both sides. And we're going to, whenever we match one of these route distinguishers from BGP, then I'm going to set the external community color to that same color up here, 6133. That's my policy. Then I come down here, this set color EVPN VPWS is actually the parent route policy, and I'm going to apply this nested L2 VPN policy, which I defined up here. Here's how I can define multiple policies in BGP. Okay, if I want to advertise multiple policies outbound, I create this parent policy and then attach multiple children underneath that one. So if I had another policy for EVPN 6134, 6135, whatever I want to do, I would just nest those up underneath here. I would create those policies up here and nest it. And you can see down here, I now set this set color EVPN VPWS down here on this address family down here on your SAFI, okay? This was the most complicated part of this. So, yes.
Question. Would the same apply L3 VPN address family?
Yes, yes.
So like if you had a node that you said everything L3 VPN related, I want to go off this link primary, you could do that.
You can do route targets as well. Yep. And obviously with the route targets, you can do filtering on those route targets and put only the specific routes that you want to identify, and now set your policy based on that route target.
You got an interesting use case.
All right, cool. All right, good. I want to hear it. All right.
Is that attachment to that peer to the
This will go to the route reflector, yes. So this peer is a route reflector, yes. Yep. Yeah, if you're not using route reflectors, I highly encourage it, unless it's a really small network like 2 nodes or something. Okay. All right, so now we're going to look at what BGP is showing. So the route distinguisher, like I was saying earlier, 198.19.1.4 with the EVI of 200. That's where we're getting it from when we define the EVI for this particular service earlier. We didn't show it here, but it was predefined for a layer 2 VPN service, and we use EVI 200. That's the route distinguisher. It says this is the path on the far side, or how we get to the other end. And this is the color they got assigned to it. So BGP is advertising color 6133 to the far end node, okay? That far end node is gonna look at that and say, hey, this path has a color 6133, I'm gonna apply that policy. We applied policies earlier with the SID list and circuit style routing, traffic engineering. It's the same kind of thing. We're going to apply this new policy, this new color to a policy, and that policy is right down here. It's an on-demand color 6133, and it just says I'm going to use SID algorithm 133. That's my constraint. Each segment, which is a layer 2 hop, is going to be a SID algorithm 133. Just follow that. If that SID algorithm says to avoid red links, then every hop out of the router, if it has a red on it, it's not going to use that link. Okay? Does that make sense?
Where was 133 defined?
133 I defined earlier in the external community. This particular algorithm was defined inside the IGP. I can show that to you. Great question. IGP. This is where we're getting to it. The role of the IGP is just to actually assign the color to the policy, or the policy to the color, okay? So we're going to advertise the policies that we're going to be running, the algos, and we're going to define those algos, how they are actually executed, and advertise them out to everybody else in the domain. Okay, so here's that 133. So router OSPF, affinity map, red. Okay, this is the color that we've been talking about. It's a different color, it's a link color. Red is the name, it's just an arbitrary name. You can use anything here. You can use your own name if you want to. Bit position 1. There's 255 bit positions, okay? We can use a whole bunch of them here. You want to use that same bit position on every router, okay? Area 0, here is that prefix SID algorithm 133 with a new prefix SID, global SID right there, 18,005. So that goes back to your question earlier. And then I'm going to go to this interface, 400 gig 0000. I'm going to say it has an affinity flex algo red. That matches up here on that affinity map. Okay? And now the actual flex algo itself inside of your IGP is right here with, we're going to do type of delay. We're going to advertise it, and we're going to do that affinity include any red. Okay? Any questions so far? All right, good deal. Let's see. Here's how you do it in ISIS. It's pretty much the same. You're still doing an affinity map. This is going to be bit position 2 on this one. Again, use the same bit position everywhere. You're going to define the flex algo. Thank you for that. And we're creating a prefix SID for the loopback. We're advertising that prefix SID there, and the affinity flex algo red is underneath the interface, saying that that interface is participating as a red interface. Okay. Before I go any further and actually execute this, is going to be a little bit longer. Any questions? Okay. Yes.
Can you go to the previous slide?
Yes, yeah.
So you're assigning a whole interface to that specific flex algo. Or so in this case, this is metric type delay. So in that case, that if I wanted a particular filter service to traverse that transit, I basically have to reserve that whole interface, right?
So what I'm actually doing here is I'm saying that Flex Algo has a metric type of delay overall, okay? And I want to also include any interfaces that are red. I don't care about the delay. Red is going to kind of override the delay. All right, so if this affinity down here does not exist on this router, then it's just going to take the lowest latency path out. But if it does include this, then it's not going to care about the lowest latency path. It's going to find all the red ones, and then of those red, find the lowest latency. Does that make sense?
Okay, so you're constraining, I guess, within the IP.
Yes, I'm preferring red above all, and then we're going to use latency after that.
You do a sub-interface here too, do you want to do multiple services?
Well, because this is inside the your IGP, this is your layer 3 link, and there's, yeah, I guess you could do sub-interfaces there, yeah.
Like a sub-interface,
Yep.
you can have like an L2 now.
Yes. Yep, you could do that. Any other questions? Yes.
If you have one policy between two nodes, you have to have unique colors, right?
You don't have to assign a color to any interface if you don't want to. You can, you know, like just for preference, if you want to assign preference to something.
It's just been architecture.
Yeah. Yeah, and that makes sense. It's whatever you feel like doing, I guess. Whatever meets your needs, but you don't have to. Yeah.
Each color has to have its own unique affinity bit?
Yes.
Okay,
Yeah.
so you only have 255 colors.
Yeah. Yes, correct. Which is a good bit for one router or for one domain. It's like 255 unique paths for unique applications in your network. Yeah. Now you can off the top of your head, any applications that you can think of that would require flex algo where you're, hey, I want to limit the latency and I want to always use specific paths. Because for me, it's one that I had as a customer, SRDF with EMC. You have to have two different paths for those guys. If you have two, like an A and a B side for your SAN, it's doing a backup replication to a remote site, and it's doing it over Ethernet. And you could use routing protocols and do some really funky stuff within BGP to prefer specific paths based off of source and destination addresses, or you can just assign an EVPN, give it a flex algo, and say always prefer for this particular service red, which is going to be for the A side of your domain, and blue for your B side, and just go. And by the way, if it fails, I'm okay with failing over, but I'd rather not. SRDF is okay with that, but it will gripe, and your SAN guy will come up to you and say, what did you do? You can also drop it, but I think he would rather have that traffic pass. Yeah. All right. Okay, here we go. Okay, good. All right, so here is the path. The service has an EVI of 200. Okay, good. I'm showing ISIS at this point. I'm showing the TMEs, they call theirs top and bottom. I think they have some paths going across the top of the topology and across the bottom. But they have, here's that flex algo 133, the priority of 200. So in case there's another one out there with a different definition with a priority of 100, I'm going to override it. But I want to use that bottom. And here's the prefix SID. 133. And I'm showing that across node 7, node 4 up here. I'm also going to show you node 3 right here. And node 2 is going to be the last one. I'm just showing that we're advertising that algorithm on all those routers.
You still prefer to use by hand?
I'm just wanting to verify for you guys. I can do every bit of this from the GUI.
No, it's just you have to go, you have to remember to go with the node.
Right.
Versus
Yeah.
Crossworks, I assume, that just pushes this everywhere.
Well, this version does not. It is assuming that the IGP is already configured. But the next version will let you configure the IGP. All right, so now I'm showing you that the different interfaces have those affinities assigned to them. There's the bundle interface, and there's a 10 gig interface. There's bottom right there on node 4. And again, after this is done, we can go and do some extra examination as much as you want.
The Crossworks that you're showing is awfully, it's like, you're doing this with like a greenfield deployment. Like there's like NSO and all that stuff is there, pushing all this stuff using policies that have been defined here.
Yes, yep.
Yeah. So-
But there, go ahead, sorry.
I was gonna say, it was like, so integrating, like we had an existing NSO, now we're trying to bring in Crossworks.
Mm-hmm.
It's kind of running into a lot of challenges.
I can see that. But there is a brownfield way. I'm surprised it's doing that. You just, as long as you have those function packs in there. So Crosswork has its own stuff. So right now, this routing policy tag, this is going to put it itself in, it's going to put this tag, which is the external community. It's going to put that in memory here. It's not going to push it out. NSO will know about it. Crosswork will know about it. But the router will not know about it until it's used. So it's things like that is kind of interesting from a Crosswork perspective that you're not going to see.
I think it's just the conflicting services, like,
Yeah.
you know, like the Delta VPN, we had to find our NSO.
Oh, yeah.
It's inside Crossworks.
Yeah, the IETF standard that is inside of Crosswork. But you can You can replace the IETF standard with yours if you need to. Yeah, you can, the brownfield migration does exist. We can make that happen for you.
Oh, yeah.
Yeah.
I'd like to see that.
Yep. All right, so there's those route distinguishers again, showing you how I'm going to be advertising this policy out to the far end. So now I'm going to create that routing policy, or I'm creating the route distinguisher first. And it was 1.2 and 1.4:200 for both of those. So I'm going to put both of them in there. If I want to do different policies or different algorithms for each route distinguisher, I can do that. I don't have to put it all inside of one policy. But since both ends are going to use the same policy, I decided to use the same route distinguisher, or both route distinguishers in the same policy here. So, yeah. I'm a little bit, I think a little bit differently sometimes. I apologize if it doesn't come out quite correct. Yeah, very much Monday morning. Thank you for your understanding. Okay, now I'm creating the route policy that is going to use that RD, and it's going to set whatever matches that RD to the community that we created earlier as well. Statement number one, so obviously with any route policy, you can have more than one statement. The condition for that, I need to match on the RD. And these are, you see only a few of these. These are tailored for L2 VPN, EVPNs. They'll have another one, it'll have a different output for a layer 3 VPN route policy. And if you just want to make a straight up route policy that you want to deploy out, you can do that as well and have different output on the screen. So now I'm pushing this to NSO, but it's not being pushed to the routers, not yet. Okay, now I'm going to create this ODN template, on-demand network template. This is essentially creating the policy, but I'm not assigning it to any services yet. I want to put that color in the name so I can recognize it easily. The head end, we have to know that, but we don't necessarily need to know the tail end on this one because BGP is going to tell us what the tail end is. And
Earlier with the PCE and bandwidth. One of our use cases, I think, for this crosswalk is going to be if in times of congestion, to be able to shift traffic.
yes,
That is possible for this, right?
yes, yes it is.
So we can take some of the services and offload them.
Yes, absolutely. And even with if you were to get into like PCA, provider connectivity assurance, it used to be a CIDIAN. So now we can do probes across that, and they're sub-second probes to see what the utilization is across the network and the latency. There's also down here, where was it, performance measurement as well. We can pull that in.
Performance measurements
Yep.
that for measuring of the
Yep. So with PCA, you can do a little bit more. You can actually, whenever a threshold is met, it'll fire off a REST API back to Crosswork to execute a policy at that point. Yep. Okay, so now I'm showing you that it's not in here. I'm pretty sure that's what I'm going to show. It's not yet in the config. I've done all this work, but nothing's in the config yet because we're not using it. There's nothing on demand. I haven't assigned it to a service anywhere, so it's not going to be used. That's exactly what I'm showing you. Nowhere in here do I see I'm going to show that, but I'm not going to show, so that was SIG algorithm 133, but we're not going to show that it's being pushed. No, there's no policy actually active on this. Next, I'm going to see there's no policy in there at all. That 6133 is not in there. These were done by the TMEs. But on either node, node 2 or node 4. That's our head end and tail end. Now we're going to come up to our L2 VPN service, and we're going to assign this policy to the service. Once we do that, we'll be able to see the traffic get redirected. So I'm going to the service. I'm going to edit that service. It's this one here, CLUS 2 to 4. Editing it. I have to go into the head end node and the tail end node. And I have to select this. I want to see everything. It turns out, right now it's just showing you what's already configured. I want to configure more stuff. So I'm going to assign this traffic engineering service mapping, ODN. I'm going to apply that policy to the head end and then the tail end. It was the L2 VPN policy. It was not the parent policy, it was the child. Here's the parent. This one I have to type in by hand. And it's going to be that set color. It's going to grab it right. Yeah, there it is. Hopefully that's going to be something that is that you use all the time, because it's the parent, and you're not going to be removing that, so it'll be something that's known to you already, so you don't have to go through all this at the CLI level. And again, I'm just showing that it's the same on both sides. It's a long-running demo, but I wanted to make sure you see everything. I wanted you to have the validation. So copy that out. Go back in, paste it. Okay, that was for node 2. Do the same for node 4. I don't have to put it on node 4 if I don't want to. If I don't want the return traffic to participate in the Flex algo, I don't have to do that.
Algo, you can, I guess if you're a service provider, you sell different tiers of service. I guess with that, so low latency, person that uses these Flex algo.
Absolutely. Instead of having to build a new policy for every single service, you just have one already ingrained inside your IGP. Yep. All right, I committed that out. That got pushed down. Now we're going to see some things change. That pushed down some configs to node 2 and node 4, including the pseudo-wire class. It's going to build that and assign that. So now we can see that before we only had one sub-policy, child policy. Now we have 2. We're going to see what that looks like. Sure. If the RD, then set the color. I'm going to do the same thing on the other node. And it's the same route policy. Again, if I wanted to be more specific, on node 4, I would look for advertisements from node 2. And that advertisement would be traffic from it. So it'd be, from node 4's perspective, it should be 198.19.1.4, because that's where it matches. Hey, this is, sorry, I'm sending traffic to 2, so I'm going to be matching on 2's RD, which is 198.19.1.2:200. All right, now I'm going to filter. So there's a lot of policies, so I'm filtering. And I wanted to look at what that traffic looks like, and there's your path. And I'm going to do the other side. Look at that. I force it to go this way because this path right here is a red link, or bottom, excuse me, is bottom. So it preferred bottom and went down to this node and then finished going the IGP path along the way. Now we'll come in and investigate just to kind of validate everything that we've seen before as well. You got the RD. I think that might be, yep, that was the end of it. So that is how you do flex algo inside of Crosswork. We saw how to do it in CLI. It's not that bad in CLI, but from a scale perspective, it's not great. Okay, from a scale of a network engineer, it's not great. But scale of flex algo is great as an idea. Like you said, if you just want to have a policy from a service provider perspective, you just set that policy and you can reassign it over and over again. But Crosswork is going to help you visualize every bit of that. And that was the goal of this. Yes, sir.
How much of these concepts port over to SRv6?
Most of them, yes. So instead of SRv6, instead of having labels, it's obviously inside of the header, the IPv6 header. You have microsids now. So there's no labels, no swapping or anything like that. You just pop off that part of the header as it's going through the path. But you still have flex algo there. You still have traffic engineering that you can do. It's just going to be microsids along the path. Yeah.
The interface to doing Crossworks is similar.
Yeah, absolutely. Every bit of it, yes. Yep. In fact, so if you noticed all those policies that were set up, there was a lot of those that were SRv6 only. So it definitely does every bit of that. Any other questions? I have 2 minutes and 50 seconds left. I'm very surprised. I thought I was going to go over it, to be honest with you. Thank you all very, very much for this. I'm going to go to the next couple of slides here, which is just, please complete your evaluations. It tells my superiors and the folks that run the technical side whether or not I should come back. So I would love to come back. If you don't mind, rate me up. But be honest at the same time. So give me feedback, however you want to do that. I would love to do this again, and if you allow me. If you have feedback, I would love to incorporate that into any future sessions. So it could help me out. Really appreciate everyone's time. I want you to have a great time here at Cisco Live. Come talk to me if you need any extra, if you want to talk about anything on the side, or whether it's Crosswork or not, we can talk about it. So continue your education. That's what we're here for. Learn. Appreciate you. Thank you.